Okay, so just to summarize where we are, so far we know how, in principle, to use, if we're given the following data, the infrared physics which is encoded in these functions, the function z gamma, in which for any particular theory, these z gamma, having this information is more or less equivalent to having what's sometimes called the Seiberg-Witten curve. So suppose some smart person has already worked out the Seiberg-Witten geometry of the theory. If you know the IR physics and you know the omega of gammas at one point of moduli space, if we know just those two things, nothing else, you don't have to know anything about the UV of the theory, you only have to know this infrared information, then we're able to determine the omega of gamma everywhere in moduli space, using this KS formula, which so far I have not proved for you. I've only told you what the recipe is. Okay, so the next two things to do are first, explain why KS formula is true, or at least one way of thinking about it. And then the second thing will be something quite different. It'll be a recipe for computing omega of gamma directly without using wall crossing. So for that, of course, I need to know something about the theory. And it'll be a kind of geometric machine in these so-called theories of class S. So the theories that you get by taking the 2-0 theory and compactifying it on a curve. So for those, we'll be able to give actually a direct recipe, which will be actually this will be a very geometric thing. Okay. So probably number 1 is today, and number 2 will be the last talk. So we got to understand, we want to understand why this formula is true, and somehow in understanding this formula, in understanding why this formula is true, really the biggest problem is just to understand what is the meaning of this automorphism. What is the meaning of these variables x gamma, and what is some physical context in which this transformation appears? Once you see where that transformation appears, you'll see sort of easily why the KS formula is true. So what we really need to do is to interpret this formula in some context. Okay, so what is that context? Well, okay, but by now there's actually a bunch of different approaches to understanding this formula. So there's a lot of different approaches to this question. I put proving in quotes because they're all physics proofs, so in one way or another, usually each proof is somewhere deficient. But so, you know, people who've worked on this, or so we worked on it, Gayato Neitzke, but also Shakoti Vafa have worked on it, Timofte, Gukov, and Soibelman have their approach, Manshot, Piolin, and Sen have another approach, and probably also others that I've unaccountably forgotten. So I'm just going to describe one approach to this thing, which is via line defects. Supersymmetric line defects. Okay. So what is a supersymmetric line defect? So let's have an example. So let's suppose that we were studying, and these are going to be things now that are defined in the UV. So let's suppose that we were studying abelian gauge theory, and I mean really abelian gauge theory, even in the UV, abelian gauge theory. Well, not even just, let's say U1 gauge theory. In U1 gauge theory, you know, what's the Wilson line operator? That's easy enough to write. L for the operator, because it's a line, is just the exponential of the integral along some path of the gauge field A. So okay, that's fine operator. That's not a supersymmetric operator. That operator would break all the supersymmetry if I put it into the supersymmetric theory. So what's the SUSY version? Supersymmetric, what's a SUSY version of this? So, sorry. So P is some path now in R4, or R3, 1. So the supersymmetric version of this, let's fix a phase. So we have this parameter which we're free to fix, and for any choice of this parameter, we're going to get a supersymmetric line operator. I'll call it L theta, and it'll be the exponential of the integral along the path. So I take A just like before, and then I have to add terms involving the scalar. So we have this, in this case, just U1 valued scalar, or sorry, not U1 valued, this real valued scalar, complex scalar, phi. And so we add phi plus phi bar, the real part of phi. Except actually we can throw in this phase, so rather than taking the real part of phi, we could take the real part of e to the I theta phi, which means doing this. So this is a little bit like something that, you know, Maldacena had introduced a long time ago in n equals 4. This is kind of n equals 2 version of that. You take the gauge field and you add to it some combination of the scalar. So then, if P happens to be a straight path, so now it really matters what this path is, then this L theta actually preserves half of the SUSY. So it preserves 4 supercharges. And in fact, let me say that a little sharper. So if, let's take this path P to be time-like. So you know, we can think of this line operator as sort of sitting at a point of space and just being extended in the time direction. It's just a sort of lump that sits at a point of space. Then the operators that this thing preserves are just exactly the operators that we called R theta and R bar theta in the previous talk. So, in other words, this line operator, or line defect, I actually rather call it a line defect. You don't think of it as an operator that acts on some Hilbert space. It's just some thing that you put in the theory that changes the theory to something else. So what this thing looks like, it preserves just the same supersymmetry as would be preserved by a BPS particle. Whose central charge had phase theta. So you should think of this supersymmetric line operator as kind of representing some very heavy external probe particle, but it's a BPS particle. It's a BPS, because it's a probe, asking what's the central charge of that particle doesn't really make sense, but we can understand kind of what the phase of its central charge is. That's controlled by which supersymmetries it preserves. So let's now make a definition. So that was an example, but let's in general say, define a supersymmetric line operator, a line defect. It's a bad habit. With phase theta to be a line defect that preserves these well, each one is spinorial, so this is 4 supercharges, R theta and R bar theta. So, you know, for example, Well, here we had this supersymmetric Wilson line. Of course, you could do a similar thing in a non-abelian theory. So in a non-abelian theory, we could have, there's a supersymmetric version of the Wilson line also in non-abelian theory, that you could also have 't Hooft operators. You could have, Wilson 't Hooft operators. So there's a classification of all the supersymmetric line operators in the non-abelian gauge theory, but this is not meant to be something that you can do only in non-abelian gauge theory. Even if you study some non-Lagrangian field theory, even if you study a non-Lagrangian field theory, well, at least we can make sense of the definition of a supersymmetric line operator. And in fact, it seems, as I'll hopefully get to say, it seems that even in non-Lagrangian theories, there actually are lots of supersymmetric line operators. Even though, since the theory is not Lagrangian, of course, you can't write a formula for them. Nevertheless, it seems that plenty of them exist. OK, so these are going to be sort of our probes. So inserting this L theta, then, I just write what I said. So it's like inserting a very heavy BPS particle at rest. It just sits like a lump at the origin. And it preserves, it's like a BPS particle whose phase is this theta. OK, great. So our point of view is that studying the theory with this thing inserted will help us study the theory without it. But let's start by asking like all the same questions that we would have asked in the usual theory. Now we ask them in the presence of this heavy sort of monster thing. Well, the first thing we can ask is, what's the Hilbert space of the theory like? What's the Hilbert space of the theory with this thing inserted? Well, it's different. I mean, it's not the original theory, so the Hilbert space is just some different Hilbert space. So in the presence of this defect, the Hilbert space is different. So the Hilbert space is modified. And so rather than just talking about the Hilbert space H, a single sort of univalent thing, now I have to talk about one Hilbert space for every line defect. So Hilbert space H sub L theta. Depends on theta, depends on L. OK. And we don't have exactly the same supersymmetry as we had before. Half of the supersymmetry is just gone. In the theory with this defect inserted, the supersymmetry algebra that acts is just half as big as the one before. The supersymmetry algebra that actually acts on the Hilbert space. And so if you now repeat this exercise of studying the representations, you get a slightly different story. So I certainly will not repeat it, but it's not too different from what I did a little bit ago. So the BPS bound becomes a little bit different. It becomes that the mass is now greater than or equal to, before it was the absolute value of z. Now, we still have a central charge operator, but the bound is now that the mass is greater than or equal to the real part of e to the I theta z. OK? All right. And so now, just like before, we could study BPS states. Now BPS states of the theory with this defect. So we'll call those a frame BPS state. Frame BPS state. So it's a state in this Hilbert space H L theta saturating this bound. And so just like before, if it saturates this bound, it means it's annihilated by the operators. Well, the only surviving operators, the only operators that exist even in the theory with this defect inserted. So these BPS states preserve all the supersymmetry that was preserved by the actual defect itself. So you should think of them as being like kind of like ground states of the defect, right? In the UV, you put in some defect. It was supersymmetric in the UV, but you can ask, you know, what is it in the IR? I mean, in principle, you could imagine that it spontaneously breaks supersymmetry, and it actually has no BPS, no supersymmetric ground states. So these are like the supersymmetric ground states of this defect. Okay. Okay, and now, so, you know, so what do they look like? They look like, well, they look like you've got this lump sitting in space carrying some charge. So they're counted. Just like before, we can introduce an index that counts these things. So I call it the framed index. I write omega with these bars to indicate that it's somehow framed. So it depends. Before, it just depended on gamma. Now it also depends on the defect, the choice of the defect. And it's just going to be, it's again a trace over the Hilbert space. Because here we don't have the broken supersymmetry, so this is actually just like Witten index. So it's literally like the Witten index that would count the ground states. These ground states don't anymore come in little multiplets, because the broken supercharges are completely gone from this Hilbert space. So here's your little index that counts the these frame BPS states. Okay, fine. So now we ask ourselves now the same question that we asked for the ordinary BPS states, the unframed ones. So we ask ourselves the question. So as with omega of gamma, we can ask ourselves, how does this omega of L theta in gamma, how does this behave under deformations? Deformation of parameters. So just like before, there's a sort of formal index argument that says, well, you know, if you change parameters a little bit, this Hilbert space is not going to change. You know, this index will not be changed by states just adiabatically moving off of the BPS bound. But just like before, it could change by if some bound states form or decay. So frame BPS bound states, well, frame BPS states, let's say. So let's say, how can a frame BPS state decay? Well, now, okay, so now this is the part that helps us. So the structure now is a little simpler than it was before. Before, we had this problem of an ordinary BPS state just decays into some bunch of other ordinary BPS states. So sort of ordinary BPS states were on both sides of that equation, so to speak. And that makes it a difficult equation to deal with. Here, the framed one, how does the framed one decay? Well, it will decay not by emitting another framed one. That's nuts. You only have one line operator there. It decays by emitting an ordinary BPS state. So the picture is like this. So an ordinary, or we sometimes call them vanilla BPS states. So what I used to call BPS states, I now, for emphasis, call vanilla BPS states, as opposed to these framed ones. So you know, so the picture is you have this framed thing, which is a big lump sitting at the origin. It's kind of stuck on this defect, and it decays. It decays into charge gamma 1 and a bulk BPS particle, a vanilla BPS particle, which is not bound to the defect, and with their charges adding up. So that's the kind of decays that we have to study if we're just interested in these frame BPS guys. And that's somehow much easier because it's kind of stabilized by this very heavy object which cannot move anywhere. Okay, so let's see in what sense is it easier. First of all, where does it happen? So it won't be a surprise where it happens. So for the usual wall crossing, when we had a vanilla particle decaying into two other vanilla particles, The place where it happened was where the two constituents had the same phase. Where the two constituents had the same phase. So here too, the issue is going to be when do the two constituents have the same phase? Well, like we said, this line defect you think of as being a heavy particle whose phase is this parameter theta. So, so the phase of this framed guy is just theta, and the phase of this one is, well, whatever it is. So argument of, I think, minus z gamma 2. Sorry, minus the argument of z gamma 2. I guess the phase of that thing is minus theta. I forget about these signs. So it's you know, it happens when some bulk particle gets lined up with phase theta. That's the moment when this decay process could occur. And moreover, now the other cool thing is that in this case, you can actually just calculate what the you can just calculate how the Hilbert space is going to change. I don't need Kontsevich-Soibelman wall crossing formula to deal with this problem. This problem was studied a while ago by, well, okay, it's very analogous to something that Denef and Denef-Moore studied. So, so we can really calculate how this framed index jumps. So we've got an index that counts the frame BPS states. We can calculate how it jumps. The reason we can calculate how it jumps is that there's a nice sort of classical or semi-classical picture of what the states look like. So the states which appear or disappear in the spectrum have a nice kind of semi-classical picture. This is what we didn't have in the more general case. Or in the more general case, the picture was somehow, there is a picture like this, but it's somehow much more complicated. But here, I can easily draw for you what these states are supposed to look like. What they look like is the following. So just at the classical level. So we've got this big heavy thing which is somehow sitting at the origin, and it's carrying some charge. Let me call that the core. And so it has charge. I'll call the charge gamma c, c for core. And then I can try to make a bound state of that to some of the BPS particles of the bulk theory. So let's draw a picture. I've got this guy sitting here, and I've got a bunch of BPS particles of the bulk theory sitting out in space somewhere. Now, if you ask, when will it happen that this configuration will be just static and BPS? Think in the approximation where these little BPS particles are kind of probes of the background that's created by this enormous heavy object in the infrared theory. Well, you can solve the BPS equations, just the classical BPS equations. And what you find is that all of these particles, they can just sit sort of stationary, but only if they're at a very particular distance from the core. So if you calculate what that distance is, it turns out to be the symplectic product of gamma h with gamma c divided by 2 times the imaginary part of e to the I theta z gamma h. Yeah. Oh, absolutely. These charges, now very good. So the frame states carry charges, which are charges, just the ordinary charges of the theory. So, I mean, despite the charge is something that you kind of measure at infinity. It's the electromagnetic flux that comes out of this thing. And those charges, the charges that are carried by these line defects are, to first approximation, just the same as the charges in the bulk theory. There's a little subtlety with that, like if the theory doesn't have any fundamentals and you put a representation in the fundamental, then its charge is not quite one of the charges of the original theory, but 2 times its charge would be a charge of the original theory. So they lie basically in the same world. They're just the charges of the bulk U1 theory. So yes, it makes sense to write that kind of symplectic inner product there. So why is there a formula like this? I mean, to make it seem a little bit plausible, let me point out that here there's sort of two different interactions going on. On the one hand, these particles, these probe particles that are out in this halo, they have a mass which depends on where they are. And the reason for that is that their mass is the absolute value of z, and z varies with the distance to this bulk. If you study the solution of the abelian theory, in the presence of this defect, the moduli move as you move in and out. So the mass of the thing depends on the distance. And on the other hand, there's also an electromagnetic interaction between the two, between the core and the halo. So balancing those two interactions is what leads to this formula for the separation distance. So there are these kind of semi-classical solutions. So sorry, this gamma h is the charge of one of the particles in this halo. So here's a state with total charge gamma c plus 6 times gamma h, for example. That's a one-particle state. It's a bound state, but it's a bound state that's kind of made up of these different kind of constituents. So now that's a classical picture. That's the classical picture. Suppose I want to know what is the contribution to the sort of quantum Hilbert space. So this also was essentially worked out by Denef, and what he found was that each of the halo particles what are the quantum states of this, represented by these classical configurations? Well, each halo particle can be in one of a few states. The number of states is this Bps index multiplied by this symplectic inner product. So how can I make sense of this? So this Bps index is roughly counting how many states does the particle itself have. And then this symplectic pairing is taking care of the fact that there's some, as we said, this symplectic pairing is exactly the intrinsic angular momentum in the field. So even though this is a static configuration, it has some intrinsic angular momentum. That intrinsic angular momentum has to be quantized, and that gives rise to this number of states.
One is about the number of halo particles, what you call halo particles. You draw 6.
I drew 6, just an example. It could be any number.
Whichever. But should they be at the vertices of a regular
No. Their position is arbitrary. Their position on that sphere is arbitrary. It's a classical solution no matter where you put them.
So the shape can also be three-dimensional.
That's right. Yeah, sorry, I sort of accidentally made it look like they're on the hexagon, but yeah. That position is also arbitrary. So what does this mean? So if I want to write the whole Hilbert space now, the whole Hilbert space of these kind of halo states, so what I have to do is generate a kind of Fock space, I can have creation and annihilation operators that create halo particles in each one of these states. Generate a Fock space. And it may be either bosonic or fermionic. That depends on the sign of omega of gamma h. A Fock space of states which sort of classically would be represented by this kind of picture. So now, so we've got these kind of semi-classical states, which are among all the states of the theory. Now, suppose I now look at, what we said was that the wall crossing was going to happen exactly when this parameter theta approaches the phase of minus z. So what does that mean for this picture? What it means is, So as the parameter theta approaches minus the argument of z gamma h, which is where this wall is supposed to be, well, you see what happens. What happens is that that radius goes to infinity because the imaginary part of that thing goes to 0. That quantity becomes real. So RH goes to infinity. And so this halo, which, you know, for most values of parameters, this halo is pretty small. This halo suddenly grows, first of all, to the size where it's very reliably treated in the infrared theory. So you can really believe that these states exist just on pure infrared reasoning. And then it actually goes to infinity. And so what happens at the moment when this thing goes to infinity is that these states just leave the Hilbert space. So this bound state literally decays by the halo particles sort of moving off to infinity. So that's a very simple picture. So it's a simple. So these states just disappear from the Hilbert space of frame BPS states. So what we want to do now is to write a formula for the effect of that. So, okay, so we just said, you know, the number of frame BPS states, the number of states, BPS states with this line defect is going to change, and it's going to change by the disappearance of these particular states. Now, what does that do to the actual numbers omega of, well, all right, that's a relatively short exercise from what if you assume everything that I told you so far. So the effect on these omegas, but it's actually not, you can write a formula, but you realize that the formula looks ugly if you write it in terms of the individual omegas. Instead, what you should do is, you know, a very common trick, you should make a kind of partition function. So let me define a partition function now, which counts these BPS states. So I make a partition function. It's just a sum over all possible charges where I keep track of the number of frame BPS states with that charge, and I multiply it by a formal variable. And that formal variable, x gamma, this x gamma now is the x gamma that's going to be this x gamma. So x gamma is this formal variable that's keeping track of the charges of frame BPS states. And now, so when theta crosses minus the argument of z gamma h, as we said, this FL theta changes. This FL theta changes because the omegas will change. The omegas change because some states disappeared from the spectrum. Disappeared or appeared, depending which way you cross the wall. But if you want to summarize what that change is, actually, that transformation is just, you can describe it as just a change of variables. So x gamma goes to x gamma times, actually, let me first write it like, so let's imagine for a second the very simplest case. This formula right now is a formula for the very simplest case where the number of halo states was just 1. And moreover, it's a fermionic state. So then why do I get this formula? It's because for every state, the coefficient of x gamma before crossing this wall is just the number of states of the line defect with charge gamma. And when you cross the wall, each one of those states picks up another state, which is a halo state, which is just a halo where I have the charge gamma, and now I have this halo of charge gamma h. In general, I would have to allow more than one halo particle, but the very simplest thing is just when there's exactly one halo state. So to every state that I add a new partner whose charge is gamma plus gamma h. And that's exactly what this change of variables does. It just says the coefficient of x gamma, I now add another state whose charge is x gamma times x gamma h. In other words, the charge of that state will be gamma plus gamma h. So this little change of variables just summarizes this wall crossing. And in general, I have a bunch of halo states. I have a Fock space. And so I just have this little generating function raised to the power. Gamma with gamma h. And this transformation is exactly the transformation that we called in the previous lecture, k gamma h raised to the power omega of gamma h. So now we see for the first time the sort of origin, the physical origin of this formula. What it has to do with is just the way that frame BPS states appear and disappear when the phase of some bulk particle gets lined up with the phase of the surface defect. Line defect. Okay. So that's the physical interpretation of these k gammas. Now, how do we use that to prove the wall crossing formula? So now we imagine doing the following thing. So now suppose we travel around some closed loop in parameter space. So what's my parameter space? I had the parameters, the actual parameters of the bulk theory. I was calling that parameter space B. And then I've also got this defect, and the defect has a parameter which was this phase, right? So that gives me an extra circle's worth of parameter. And so this is the B cross S1 that appeared in the previous lecture. That circle gets now interpreted as the phase of this line defect. So suppose we travel around now a closed loop in the parameter space. So here's again the picture. So here again I'm drawing the phases of the bulk BPS states. Whatever the BPS states are in the original theory. If I start here with some, at this particular value of parameters, with some line defect. It has some frame BPS states. Now I travel around a loop. At each of the walls that I encounter here, some frame BPS states will appear or disappear, and it'll happen exactly according to this formula. They're just the halo states that are made out of the bulk BPS states. So frame BPS states appear and disappear in some complicated way according to this formula. But when I come back to the original place, I must have the same frame BPS states as I had before. So the generating function, f of L theta and x gamma, must return to its original value. Just because it's well defined. It is just the generating function of frame BPS states for that particular operator at that particular point. So this complicated product of automorphisms now. So if I travel around this path, this loop P, it's a product over all the places where P intersects, C, just like I wrote before. In this case, it would be a product over 5 places. The composition of those 5 automorphisms that's some transformation of variables which has to preserve this little generating function. Now what we'd like to conclude is that this product is actually the identity. That was the KS wall crossing formula, was that this complicated product of automorphisms should actually be the identity. So for that, we need to know that the theory has actually some line defects in it, right? So if the theory has enough line defects in it, so that, for example, any x gamma is a linear combination of the L theta for various L. Then this is really enough to prove that this product, this crazy product of automorphisms, is the identity, which was this KS formula.
Clarify what you mean by the parentheses.
Which parentheses? Oh, yeah. X gamma is a formal variable, right? So I've got a bunch of different L's, right? I've got a bunch of different line defects. Each one of them has some generating function, which is some combination of X gammas, right? So for example, let me give you an example. So for example, let me write, since the sort of first Argiers-Douglas theory, the one that was studied originally by Argiers and Douglas. So in this theory, so I'll just write some things that I happen to know, and then we'll see how they fit into this statement. So in this case, so the charge lattice is two-dimensional. So let's introduce two variables. Just x gamma 1 is, call it x, and x gamma 2, let's call it y. And then we have, in this theory, it's kind of funny. There's actually five natural line operators in the theory, line defects, which have something like f of L1 is just x, f of L2 is like x plus y or x plus xy or something. And then, I forgot the other three, but it won't matter. What's that? Right, I've got enough already, exactly. I don't need the rest. So the point is, right, if I have some automorphism of these formal variables, which preserves all of these things, then first of all, it preserves x, and once I know it preserves x, if it also preserves f of L2, I can show that it also preserves y, right? If it preserves x and preserves that thing, then it preserves y. Because it's an automorphism, it actually preserves also the sort of multiplicative structure. So that's enough. Now, and like in non-abelian gauge theories, you certainly have enough line operators because roughly the weights and co-weights that label the Wilson-Tufte operators, there's the lattice of them is the same dimension as the lattice downstairs. So it sort of experimentally, it seems that in every quantum field theory where you're able to answer the question, the theory actually has a lot of line operators. And what I mean is it has enough line operators for this to work. Or another way of saying it is that the number of line operators that you see in the UV is the same as the number of line operators that you see in the IR. So the infrared theory is just an abelian theory. It has, it's easy to write down what its line operators are. Somehow the number of those, you could think that all those are just accidental. There are some things that exist in the IR, but they don't come from anything in the UV. And that seems to be wrong. It seems that the number of UV line operators is the same as the number of IR line operators. It's kind of a deep thing, which I don't think has been fully understood. I mean, there should be a sort of general reason why that's true. It's a little bit like sort of topological invariance. It's like saying you can compute some supersymmetrically protected partition function. You can compute it either in the IR or in the UV. Here, what you compute is not a number, but it's the space of line operators, and that space is kind of the same size in the IR and the UV. Anyway, assuming that that's the case, then that finishes the proof of why the wall-crossing formula is true, because you see now what these automorphisms mean. What they mean is literally, what they are literally is how this generating functions of frame BPS states transform. So somehow the right object to look at to understand this formula is not the ordinary BPS states. The ordinary BPS states themselves form some very complicated structure, but that structure is represented on the frame BPS states in a simple way. So it's also a little bit like, okay, if you allow me one more sort of vague comment, it's a little bit like studying a group. A group is a very complicated thing. What you tend to do is study rather its linear representations. And here we're studying the BPS states. The BPS states are somehow very complicated, but we can understand them by understanding how they are represented on the frame BPS states. Yeah. No, in any particular theory, you can do it in any particular way. So in the Argyres-Douglas theories, at least in these examples, we did it using kind of geometric, sort of six-dimensional engineering of the theory. For ordinary gauge theories, for ordinary non-abelian gauge theories, you can just write down directly the Wilson-Twift operators and see that you have the right number of them. But no, as a totally general thing, I mean, that's part of the mystery. A totally random theory, it would seem sort of surprising that it would always have the right amount of line operators, but somehow it does. Okay. So now I'm in a tricky spot because I got about 15 minutes, and I now have to start on this sort of totally different thing. But I think I'll just do that. So let me begin to tell you about this other machine for finding the BPS spectrum. So now I'm done talking about the wall-crossing formula. And I want to tell you sort of, suppose that you didn't know the spectrum even anywhere, and you wanted to understand just from first principles, what are the BPS states? I want to try to tell you a machine which enables you to do that. And I guess what I'll do is I'll get as far as sort of setting up the kind of basic data. Unless there's more questions about that, about the last thing.
You said there are many different approaches to looking at this. So what would be another best line operator?
Oh, yeah, an approach that doesn't use the line operators? Oh, yeah, OK, maybe that's more fun. Yeah, let me tell you one other approach. Right, so I could study the following thing. I could say, I have this n equals 2 theory in 4 dimensions. I have this n equals 2 theory in 4 dimensions. I want to study something where the effect of the BPS states will become kind of visible. I want to represent them on something. Here I represented them on the frame BPS states. Now I want to represent them on something else. So let's do the following. Let's take the n equals 2 theory. And rather than studying it on R4, let's study it on R3 times a circle. So what is that theory like? It has, what is that theory like in the infrared, let's say? Well, how could I get at that question? The most naive thing I could do is I could take the Lagrangian, the infrared Lagrangian in 4 dimensions, and just take the dimensional reduction of that infrared Lagrangian. So the sort of first approximation would be to take the IR action in 4 dimensions and just dimensionally reduce on a circle. What will you get in this way? So the infrared theory in 4 dimensions, as we said, was a U1 to the R gauge theory with n equals 2 supersymmetry. If I dimensionally reduce it in 3 dimensions, I will also have I'll have the same amount of supersymmetry, and I'll have a U1 to the R gauge theory, but then in 3 dimensions, I could always dualize the gauge fields into scalars. So let's do that. Let's dualize the gauge fields into scalars. So then the theory that remains in 3 dimensions will be just a sigma model. So we're left with just a sigma model. Now, what is that sigma model? Well, what is the target of the sigma model? It's pretty easy to describe it in this first approximation. What it is so what do we have? We have the scalars that we had in 4 dimensions. Those scalars were parametrizing the Coulomb branch. And then we have the new scalars that come from dimensional reduction. Well, there was one scalar which was the holonomial of the gauge field around the circle. well, one for each gauge field. So that gives me a bunch of circles, because the U1 holonomy is circle valued, right? So that gives me a bunch of R circles. And then from dualizing the gauge field, I get another R circle valued scalars. So altogether, what I get is a torus. For every point of the Coulomb branch, I now have this torus over it, which is given by the abelian gauge fields after dimensional reduction. So here I have the base, which is of real dimension 2R. And here I have this extra torus, which comes from the gauge fields, which is also of dimension 2R. So I've got a sigma model into this kind of torus bundle over the moduli space. This torus bundle is sometimes called like the Seiberg-Witten integrable system. The constraints of supersymmetry tell you actually something quite strong about the sigma model. It tells you that the target space has to be actually hyperkähler. So a very strong constraint on its metric. It has to be hyperkähler. And now you ask yourself, well, okay, that was the first approximation. Now, what are the quantum corrections to this first approximation? And there's one obvious quantum correction that you need to take care of. And what is that quantum correction? It comes from an instanton, which you can describe as you take the BPS particles of the theory in 4 dimensions, and you have them going around the circle. That gives you a kind of instanton, which corrects the 3-dimensional theory. So corrected by. So it's corrected by instantons, which are loops. So it has to be a BPS instanton. So it's a BPS particle. BPS particles of the 4D theory going around the circle, which I'm calling it S1 sub R now. It has radius capital R. What's the size of these instanton corrections? Well, the size of the corrections is roughly e to the minus the action of that instanton. So it's e to the minus the mass of the particle, which is absolute value of z, times the distance that it goes around, which is r. So there's correction. So you have this sort of naive dimensional reduction action, which is real simple, and then it has corrections which are of this order. So now you go and compute the corrections. You try to compute the corrections, and you run into an obvious puzzle. The puzzle is, on the one hand, this action, this 3-dimensional theory, whatever it is, it shouldn't have a phase transition in it, because the 4-dimensional theory didn't have a phase transition. So whatever the 3-dimensional Lagrangian is, it has to be just smooth. So this quantum corrected action, which is a quantum corrected hyperkähler metric. So we have now some quantum corrected hyperkähler metric on this torus bundle over the base. We have this quantum corrected hyperkähler metric, and it has to be smooth. It has to be smooth just on totally general grounds. There's no phase transition. Now, on the other hand, if you just compute the corrections naively, you would think that the corrections will have some discontinuity, because the corrections come from these BPS particles, and when you reach a wall, the BPS particle suddenly disappears. So the correction due to that particle would suddenly disappear. And that looks like it's in danger of making this metric be discontinuous. And the resolution is that requiring this metric to be smooth is actually turns out to be equivalent to the Konsevich-Soibelman formula. So when you work out the correction carefully, you find that in addition to the one-particle corrections, there's multi-particle corrections, and those corrections all conspire to make the metric smooth. only if this KS formula is satisfied. So that's another way of understanding why the formula is true. Again, you take these BPS states and you don't study them directly, you represent them on something else. In this case, the something else that you represent them on is the Lagrangian of the dimensionally reduced theory. So this is kind of a fun thing. So the connection between, I should at least try to say the connection between this and the previous story. So if you wanted to relate this directly to the line operators, goes by, if you study the functions, if you consider now, so if we have a line operator and we wrap it on the circle, we could consider now its vacuum expectation value. So we've got our theory on a circle, and we have this line operator, or line defect, which we could actually wrap around the circle. So this is a function on this hyperkähler moduli space. And supersymmetry, in this case, tells you it's a holomorphic function. Well, holomorphic, but holomorphic in which complex structure? It's hyperkähler, so it has a lot of complex structures. It's holomorphic in the complex structure labeled by e to the I theta, for those who know about hyperkähler manifolds. Anyway, so I told you two ways of deriving this formula. They sounded totally independent, and I only sketched one of them. But the relation between them is, goes by considering the vacuum expectation values of the line operators. And this turns out to be something cool, actually. It's connected to a very interesting structure on this moduli space. But OK. I was told that construction will begin sort of at 6. So.
So we have time to take questions until the hammering starts. So, starts. So, please. Actually, I had a question about so this constraint from the conservative formula that the loop operator must be 1.
Yeah.
Does it still hold when you have singularities in the moduli space with some monodromies?
You always have to be a little careful with this. If there's a singularity in the moduli space and you go around that singularity, then it still has to be 1, but you have to take account the monodromy of the local system in understanding what that statement means. So there is still a constraint. There is still a constraint, but how you state that constraint depends on how you think about that monodromy. Yeah. Yeah.
Does it mean that somehow with this probe approximation capture the whole crossing?
Well, no, it doesn't. I mean, what it means is that, yeah, so it's funny. So this frame, this probe picture seems to be good enough to capture the wall crossing of these framed states. Now, if you tried to use that picture directly, to use the same kind of picture directly to study the wall crossing of the unframed states, you find you'd have to consider much more complicated kinds of pictures. So in this picture, we were helped a lot by the fact that we had one state, which was just the core, which was frozen at the origin and couldn't go anywhere else. If you try to draw analogous pictures without having that core there, in other words, if you tried to study just the ordinary wall crossing directly without this framing business, you would be drawing much, much more complicated pictures. And I don't think anyone has managed to get the Conceivus-Soibelman formula directly in that way. So it's always, it is this funny kind of two-step thing where you introduce a simpler object whose wall crossing is easier, more under control, and then you use that to get constraints on the more complicated thing. But it's not that you can study the whole thing directly in the semi-classical picture. At least I don't know of, I don't know everything that people have done. But did you guys do that in some form?
I think we can.
What's that?
I think we can.
Yeah. So okay.
The quantum mechanics of this interacting states, of the bound state.
Okay. So I withdraw the part of my answer, which was, I don't think anyone can do it that way. I guess it has been done that way, but that's not what I just did.